Fine. So we have already, did these things that angles in the same segment are equal. Angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle, right? So if there is an arc AB which subtends an angle theta at the remaining part of the circle, right? Then at the center it will subtend an angle 2 theta. We have already proved this in our first session of circles. So here this is a major arc AB. So this subtends theta on the circumference. So this will subtend 2 theta at the center. Okay. An angle in a semicircle is a right angle. This also I think we have done, because if AB is the diameter, then you know that angle at the center is 180 degrees. So angle at the circumference will be half of 180. That will be 90. So angle ACB would be 90 and angle ADB would also be 90 degrees. Fine. So both these angles will be 90 degrees. So angle in a semicircle is always 90. In fact, you can see that this angle will also be 90, right? Because AB is the diameter. So this is a semicircle. Angles in the same segment of a circle are equal. This also we have done it in the first session. We have also proved it. So if this angle is theta, then this angle is also theta. Not only this, you can take any point. So all these angles are equal to theta. Okay. Similarly, this is a major arc AB which is subtending theta on the circumference. So at all the points it will subtend theta. Okay. So all these angles are equal to theta. Okay. Now let us study the converse of the above statement, right? What is the converse? First of all, the above statement is that angles in the same segment of a circle are equal. So now let us try to understand its converse. So if there is a line segment joining 2 points, okay, so let us consider a line segment, say AB, it is joining 2 points AB. So line segment joining 2 points subtends equal angles at 2 other points lying on the same side of line segment. Okay. So this line segment AB subtends equal angles at 2 other points. Say there are 2 other points P and Q which are lying on the same side, of the line segment. What do you mean by same side? Here P and Q are on the opposite side. So if I take a point here and a point here, then these 2 points are on the opposite side of this line segment. Okay. So if there are 2 points on the same side of the line segment, okay, and if the angle subtended by this line segment at these 2 points, what do you mean by angle subtended by line segment AB at point P? That is angle APB, right? And angle subtended by line segment AB at point Q is angle AQB. So if these 2 angles are equal, okay, if these 2 angles are equal, then this theorem says that the 4 points are concyclic. That is, you will have a circle which passes through all these 4 points. Okay, this is what we need to prove. Is it clear? So let us do one thing. So what I'm doing is, I'm taking a line segment, say PQ. Okay, so there is a point R and angle PRQ is equals to angle PSQ. Okay, so it is given that angle PRQ is equals to angle PSQ. Then we need to prove that PQRS are concyclic. Concyclic means they lie on the same circle. Okay, so let us do one thing. Let us draw a circle which passes through P, Q and R. Right, through 3 non-collinear points we can always have one circle. So I'm drawing a circle which is passing through P, Q and R. So draw a circle passing through P, Q and R. Okay, so let us say the point S does not lie on this circle. Okay, if point S lies on the circle, the statement is proved. So say S does not lie on the circle. Okay, so let us say this point S dash, okay, which lies on the circle. So here the intersection of PS, I mean, say the circle cuts this line segment PS at S dash, okay. So this line segment PS is cut by the circle at point S dash. So let us join this, okay. Now since this is a circle and this PQ will subtend same angle, right? This PQ will subtend same angle at two different points on the circumference. So angle PRQ should be equal to angle PS dash Q. So this implies angle PRQ is equals to angle PS dash Q, right? But it is given, that angle PRQ is equals to angle PSQ, right? This is what it is given to me, that these two angles are equal, okay. So but S dash lies on the circle, so these two angles are also equal. So this implies that angle PSQ is equals to angle PS dash Q, okay. So that is these two angles are equal. Now consider this triangle QSS dash, okay. So if you consider this triangle QSS dash, you will see that this angle is an exterior angle, whereas this is an interior angle. So this angle QS dash P should be in fact the sum of this angle and this angle, right? So these two angles can't be equal in a triangle actually, because these are exterior and interior angles, okay. So from triangle QSS dash, comma, angle QS dash P is exterior, comma, angle QSS dash is interior, and these two are equal. So this is a contradiction, okay. So this is a contradiction. So it means that our assumption is false, okay. Our assumption itself is false. So this implies that our assumption is false. This implies that S must lie on the circle, okay. So I'm not writing here because there is no space. So finally this implies that S must lie on the circle. So that is P, Q, R and S are concyclic points. Is it clear? So if there is a line segment PQ which subtends same angle at two different points, and these 2 points should be on the same side of the line segment, so then these all 4 points will be concyclic. That is, if you draw a circle through PQ and R, this circle will definitely pass through S also, okay. If I draw a circle through PQ and S, then this will pass through R also. So these 4 points will be concyclic, okay. So it is the converse of the above statement, that is angles in the same segment are equal, okay. This is true, but if there is a condition that a line segment subtends equal angles at two different points, then all these points should lie on a circle, okay. So let us move forward. Yeah, so solve these two questions. You need to find angle AOC here in the first one and angle BAC here, okay. So here this one and here this one. So quickly solve it, and if you get the answer, let me know it in the chat. Okay, so let us discuss. This is pretty straightforward problem. So here OA and OB are radius, right? So this angle will also be 30. So similarly OC and OB are radius, so this angle will also be 40. So now this RKC subtends 70 at the circumference. So at the center it will be 140. And in this question we need to find this angle BAC. So first let us find the central angle. So this is 110, this is 90, that is 200. So the central angle is 160. This implies angle BAC is half of 160, which is 80 degrees. Fine. So just quickly copy it down. 10 seconds to copy it down. Then we'll move forward. Yes. So let us move forward. Yeah. Solve this question. So here you need to prove that side length BC is equals to the circumradius of the triangle ABC. What is circumradius of triangle ABC? It is nothing but the radius of circumcircle. Yes, so pretty straightforward problem. Let us join BO and CO. So join OB, OC. Okay. So angle BOC is how much? 60 degrees. And since OB is equals to OC, so this implies that triangle OBC is equilateral, right? So this implies that BC is equals to OB. That is the circumradius, right? So BC is equals to OB, which is equal to circumradius of triangle ABC. Yeah. So quickly copy it down. 10 seconds to copy it. Yes. Let us move forward. Solve these two questions. So you need to find angle BAC here, and here you need to find angle PQB. O is the center, okay? O is the center. So if you get the answer, let me know it in the chat. So solve both the problems. Okay, so many of you have solved it. Let us discuss. So this angle is the exterior angle of triangle, right? So this 130 should be sum of this and 20. So this angle is 110. Okay. Now this arc BC subtends 110 here. So at A also it will subtend 110. Okay. So this angle is 110. So this angle is also 110. Now in this question, what happens is, since O is the center of the circle, so this is a semicircle, and we know that angle in a semicircle is how much? 90 degrees, right? So angle APQ is equals to 90 degrees because it is angle in a semicircle. So this implies angle PAB, it is 90 degrees minus 42, that is 48 degrees, right? So if this is 90, this one is 48. Now this arc subtends 48 here, so this will also subtend 48 at Q. Okay, so this implies angle PQB is also equal to 48 degrees. Fine, let's move. Yeah. Solve this question. So AP is equals to CP is given. You need to prove that AB is equals to CD. Okay, so I'll give you a hint. Try to prove the triangle APD is congruent to triangle CPB. Okay, so try to prove that these two triangles are congruent. Okay, so let us discuss this one. So consider arc AC. Okay, let us write it in this way. Arc AC. Okay, so we are considering this arc. So this will subtend equal angles, right? These angles will be equal. So angle ADC would be equal to angle ABC. Okay. Also, angle APD is equals to angle CPB because these are vertically opposite angles, and these were equal because these are angles in same segment. Okay. So also AP is equals to CP, right? This is given. So this implies that these two triangles are congruent. Triangle APD is congruent to triangle CPB by AAS axiom. Okay, so this implies that PB is equals to PD, right? So if you just add these two equations, that is AP is equals to CP and PB is equals to PD. So if you add these two equations, simply you will get AB is equals to CD. Okay. So just try to remember this idea. Whenever two chords intersect in this circle, we'll also use this idea later on when we'll study about secants and tangents. So if two chords intersect in a circle like this, so then this arc subtends this angles, right? So these two angles are equal. Similarly, this arc subtends this angles. Okay. So these two angles are also equal because this chord BD subtends angle A and angle C. So these two angles are equal. And also if you see this chord, then these two angles are equal. Okay. And these two angles are equal because these are vertically opposite angles. So if two chords in a circle intersect like this, then these two triangles will definitely be similar because angles are all equal. Okay, so this angle is this angle and this angle is this angle. So these two triangles will definitely be similar, but here it is also given that these two sides are equal. So these triangles were congruent in this case because it was given that AP is equals to CP. Else these two triangles will definitely be similar. So just remember this idea. Okay, let us move forward. Yeah, do this one. So there is an isosceles triangle, say ABC, and AB is equals to AC. So BC is the base of an isosceles triangle, and it is given that you are drawing circle with ABS diameter or ACS diameter. Say this is a circle with ABS diameter. Okay, so okay, so let us say this cuts BC at some point D. So you need to prove that this bisects BC, that is BD is equals to DC. This is what you need to prove. This is an isosceles triangle. Okay, so this is a circle with AB as diameter. So it is a pretty straightforward problem. Since AB is the diameter in the circle, we know that angle in a semicircle is how much? 90 degrees. So angle ADB is equals to 90 degrees because it is angle in semicircle. Okay, semicircle. So that is AD is the altitude of isosceles triangle, and we know that in an isosceles triangle the altitude is also the median. It is also the angle bisector because these two triangles would be congruent by the right angle, hypotenuse, and side congruency. Okay, so triangle ABD is congruent to triangle ACD by right angle, hypotenuse, side. This implies that BD is equals to DC. Okay, so the fact which we use here is the angle in a semicircle is always 90 degrees. So let us move forward. try to do this one. So let us do this. So ABC and ADC are two right triangles with common hypotenuse AC. Okay. So say this is AC. ABC is 90 degrees and also ADC is 90 degrees. Okay. So we need to prove that angle CAD is equals to angle CBD. This is what we need to prove. Okay. So angle CAD is equals to angle CBD. This is what we need to prove. Okay. So try to observe if there is any circle forming in this figure. So just if I draw a circle with AC as diameter, okay, let us say draw a circle with AC as diameter. Okay. I mean, if there are 2 points, then you can draw a circle with these 2 points as diameter, right? Because if there are 2 points, then the center of the circle will be the midpoint of AB and the radius is half of AB. So with that center and radius, you can draw a circle with any 2 points as diameter. So if you draw a circle with AC as diameter, I know that this will pass through B and also it will pass through D, because angle in a semicircle is 90 and angle ABC is 90, so it will pass through B, and angle ADC is also 90, so it will pass through D. Okay. So this implies the circle passes through B and D. Fine. So angle CAD is this one and angle CBD, that is this angle. Okay. So this angle and this angle you need to prove they are equal. So they are equal because they are the angles in same segment. Fine. For DC only subtends both these angles. So they are equal. So angle DAC is equals to angle DBC because these are angles in same segment. Fine. So we have just drawn a circle with AC as diameter, and since these angles are 90 degrees, this will pass through both B and D. And once we have got the circle, then we use the theorem that angles in a same segment are equal. So just quickly copy it down in 10 seconds. Fine. So let us move forward. Yeah. So we have already discussed what is a cyclic quadrilateral. We have also proved that the opposite angles in a sum of opposite angles in a cyclic quadrilateral is 180 degrees. So let us discuss a bit more about cyclic quadrilaterals and let us solve some problems. So what is a cyclic quadrilateral? If all the four vertices of a quadrilateral passes through a circle, then this quadrilateral is a cyclic quadrilateral. Okay, we know that if there is a triangle ABC, then we can definitely have a circle which passes through all these three vertices. Because if there are three non-collinear points, you will have exactly one circle which passes through all these 3 points. But if there is a quadrilateral, there is no guarantee that these all the 4 vertices will lie on a circle. Okay, that also means that if you draw a circle through any 3 vertices, right, I mean you can draw a circle through A, B and C, it may not pass through D. Okay, so if you draw a circle through A, B and C, right, I'm trying to draw a circle through A, B and C, and if it also passes through D automatically, then this quadrilateral is cyclic. That is, all the vertices lie on the same circle. Okay, so you can also interpret this in this way, that if you try to draw a circle through any 3 vertices, okay, through any 3 vertices, if you try to draw a circle, then if that circle also passes through the 4th vertex, it means that these 4 points are concyclic. That is, the points lie on the same circle. So the points lying on the same circle are said to be concyclic points. So then this quadrilateral ABCD is a cyclic quadrilateral. So we have already proved that sum of each pair of opposite angles is 180 degrees in a cyclic quadrilateral. That is, angle B plus angle D is 180 and angle A plus angle C is 180. Okay. So this thing we have already proved. Yeah. So the converse of above statement, that if in a quadrilateral, suppose you have a quadrilateral ABCD, okay, and it is given that sum of opposite pairs is 180. Okay, that is, angle A plus angle C is 180 and angle B plus angle D is 180. This is given. So then you need to prove that quadrilateral ABCD is cyclic. Okay, so this is the converse of the above statement. So in a cyclic quadrilateral, the sum of opposite angles is 180, and if in any quadrilateral, the sum of pair of opposite angles, that both the opposite angles are supplementary, then you can say that this quadrilateral is a cyclic. So how will you prove this? So I mean, let us draw a circle passing through 3 points ABC. Okay, say it doesn't pass through D. So draw a circle through 3 points A, B, C. Okay, so let D does not lie on that circle. If D lies on that circle, then it is definitely cyclic. So let D does not lie on that circle. Okay, so I mean, I think now you can do this by the same logic what we have used to prove the converse of the statement that angles in a same segment are equal. So let us say this point is D dash. We know that angle B plus angle D dash is equals to 180 because AB C D dash is cyclic. Okay, since this quadrilateral is cyclic because all these 4 vertices are lying on a circle, then this plus this is 180, and it is given that angle B plus angle D is 180. Okay, so angle B plus angle D is 180 is given. So this implies angle D is equals to angle D dash, and if you consider this triangle, okay, ADD dash, then this is an exterior angle of this triangle. Okay, so angle AD dash C is exterior angle equal to interior angle ADC. So this is a contradiction. Okay, so this is not possible. That D doesn't lie on this circle is not possible. D has to lie on this circle. Okay, so this simply implies that D lies on the circle. Means our assumption is false, right? Because we arrived at a contradiction. Because then we can say that our assumption that D doesn't lie on the circle, this is false. Okay, so D must lie on that circle. It means that ABCD is a cyclic quadrilateral. So if you draw a circle through 3 points, this will definitely pass through the fourth point D. Okay. So if in any quadrilateral the sum of a pair of opposite angles is 180, then that quadrilateral is cyclic quadrilateral. So if any side of a cyclic quadrilateral is produced, then the exterior angle is equals to opposite interior angle. So this is pretty straightforward. So let us say ABCD is cyclic quadrilateral, okay, and DC is produced to P. So we need to prove that angle BCP, that is this exterior angle, is equal to opposite interior angle, that is equal to angle DAB. So let us prove it. So angle DCB plus angle DAB is 180. We know this because ABCD is a cyclic quadrilateral, right? That is this angle plus this angle is 180. Also this angle plus this angle is 180. Okay. Angle DCB plus angle BCP is 180 because this is a linear pair. So this implies that angle BCP is equal to angle DAB. Okay. So in any cyclic quadrilateral, if you extend one side, then the exterior angle is nothing but it is equal to the opposite interior angle. So just quickly copy it down, then we'll move forward. Fine. So let us move forward. So let us discuss the Ptolemy's theorem for a cyclic quadrilateral. Okay. So what this theorem says is, if ABCD is a cyclic quadrilateral, okay, if this is cyclic, means there is a circle which passes through all the 4 vertices of this quadrilateral, then sum of product of opposite sides is equals to product of diagonals. Sum of product of opposite sides means what? AB times CD, this is product of opposite side, and DA times BC, this is product of opposite side. Sum of this, that is AB times CD plus BC times AD. Okay, so this is sum of product of opposite sides. Fine. This is equal to product of diagonals, that is AC into BD. This is true for what? For cyclic quadrilateral. Okay. So in cyclic quadrilateral. Okay. So in cyclic quadrilateral ABCD, this is true. That is AB into CD plus BC into AD is equals to AC into BD. Okay. So out of these 6 lengths, these are the 6 lengths of the quadrilateral, 4 sides and 2 diagonals. If any 5 of them are given, then you can automatically find the 6th length. Okay. So we'll see the uses of this theorem later. Okay. We'll solve problems on this theorem. So this is very important theorem. You need to remember it. So I will not go into the proof of this theorem. If possible, we'll get into the proof at some later stage, but not now. Okay. So for now, just remember this. And for a non-cyclic quadrilateral, this inequality holds. That is, this is greater than or equal to. So AB times CD plus BC times AD is always greater than or equal to AC into BD. But for a cyclic quadrilateral, this is equal to. Okay. Fine. So let us move forward. Yeah. Solve this question. So here in this triangle ABC, you are given AB is equals to AC and angle ABC is 50. You need to find these 2 angles. And here you need to find angle DCP. Yes, if you get the answer, then let me know it in the chat. Yes, so many of you have already solved it. So ABC is 50, and since AB is equals to AC, this implies that ACB is also 50. Okay. So this finally implies that angle BAC is 50, 50, 100. So this is 80 degrees. So if this is 80, then this arc will subtend same angles, right? So angle BDC is also 80. So this implies angle BDC is 80 because the angles in same segment. And BDCE is cyclic, right? BDCE is cyclic quadrilateral. So angle BEC is 100 degrees because opposite angles are supplementary. So this angle would be 100 degrees. Okay. So in this question, you need to find angle DCP. So first let us find angle BAD, this angle. So this is how much? 70 degrees. That is half of 140 degrees. And since ABCD is cyclic quadrilateral, because all the four vertices are on a circle, so this implies that angle DCP, this is exterior angle, it is equal to opposite interior angle, that is angle BAD, that is equal to 70 degrees. So this angle is how much? 70 degrees. Fine. So let us just discuss it one more time, because this is the first problem in cyclic. So here AB is equals to AC was given. So since this angle is 50, then this angle is also 50. Now if these two angles are 50, then this angle is 80, because in a triangle sum of all angles is 180. Now if this angle is 80 degrees, then this angle is also 80 degrees, right? Because these are the angles in same segment. Now if this is a cyclic quadrilateral, then this angle is 100 degrees, because sum of these two should be 180. And here this BD subtends 140 at center, so this subtends 70 at the circumference. Okay, and ABCD is cyclic quadrilateral, so this exterior angle is equals to opposite interior, which is 70. Fine. So let us move to the next question. Yes. So prove that cyclic parallelogram is a rectangle. Cyclic parallelogram means there is a parallelogram which is cyclic quadrilateral. Okay, so all the four vertices of a parallelogram lie on a circle. So you need to prove that it will be a rectangle. Pretty simple one. 2 minutes for this. Okay, so let us discuss. Pretty straightforward. So there is a parallelogram ABCD. Okay, so parallelogram ABCD. We know that in parallelogram, opposite angles are equal, right? Angle A is equals to angle C. And since it is cyclic, the sum of opposite angles is 180. That is, angle A plus angle C is 180. So this implies that angle A is equals to angle C is equals to how much? 90 degrees. And similarly, you can tell that angle B is equals to angle D is equals to 90. So since all angles in a quadrilateral are 90 degrees, it is a rectangle. Okay, since all angles in a quadrilateral are 90 degrees, it is a rectangle. Fine. So quickly note it down, we'll move forward. Yes, let us move forward. Yeah, do this one. Prove that the quadrilateral formed by angle bisectors of a cyclic quadrilateral is also cyclic. Right. So there is a cyclic quadrilateral. Say ABCD. So the angle bisectors of this one. So say this is the angle bisector, this is the angle bisector, this is angle bisector, and this is angle bisector. Okay. So this is A by 2, this is D by 2, this is C by 2, and this is B by 2. So this is PQRS. Okay, so you need to prove, required to prove that PQRS is also cyclic. Fine. It is given that ABCD is cyclic. So to prove a quadrilateral cyclic, what we do is we prove that the sum of opposite angles is 180 degrees. Okay. So let us prove that angle Q plus angle S is 180 degrees. So angle Q is how much? 180 degrees minus A by 2 minus D by 2, right? From this triangle. And from this triangle, I can say that angle S is how much? 180 minus B by 2 minus C by 2. So angle S is equals to 180 minus B by 2 minus C by 2. So angle Q plus angle S is how much? 360 minus A plus B plus C plus D by 2, which is 360 minus 180, which is 180. Fine. So this means that sum of opposite angles is 180. This implies that PQRS is also cyclic quadrilateral. Okay. Yeah, so let us move forward. So if two sides of a cyclic quadrilateral are parallel, then prove that remaining two sides are also equal and diagonals are also equal. So try this question. So say this is your cyclic quadrilateral ABCD and AB is parallel to DC. So you need to prove that BC is equals to AD and AC is equals to BD. Diagonals are equal and remaining two sides are also equal. Yes, so take 2 minutes of time, then we'll discuss. Yes, so let us discuss this one. So first let us join this DB and AC. Okay. So what I'm trying to do is I will try to prove that these two triangles are congruent. That is, triangle ABD is congruent to triangle ABC. This is what I'll try to do. So angle ADB is equals to angle ACB because these are angles in same segment. ACD because these are angles in same segment. Fine. Okay. Also, angle B plus angle C is 180 because these are co-interior angles, right? Since AB is parallel to CD. Okay. AB is parallel to CD and this is a transversal, right? So sum of these two angles on same side of transversal or the co-interior angles are supplementary. So angle B plus angle C is how much? 180 degrees. Also angle A plus angle C is 180 degrees because ABCD is cyclic quadrilateral. So the sum of opposite angles is always 180. So this implies that angle A is equals to angle B. Okay, these two angles are equal. That is, this angle is equals to this angle. Okay. So now if you see these two triangles, that is ABD and triangle ABC, you can see that these two are congruent because these two angles are equal. Okay. And AB is the common side. So these two are congruent by AAS. So this implies that BC must be equal to AD and AC must be equal to BD. Find the corresponding parts. This should be equal and this should be equal. Okay, so quickly copy it down. Yes, let us come back to previous question. Here we need to prove that angle bisectors form a cyclic quadrilateral. Okay, so if you look at the proof, what we have done is simply this is A by 2, this is D by 2. I mean, we have marked all these angles and then we have wrote that angle Q. Angle Q means angle AQD. This is 180 minus A by 2 minus D by 2, which is fine. We wrote angle S is 180 minus B by 2 minus C by 2, which is also perfect. And angle Q plus angle S we got as 180. Okay. So in this entire process, did we use the fact that ABCD is cyclic? In this entire process, we didn't even use the fact that ABCD is cyclic. Okay. So I mean, this is true for any quadrilateral, not only for cyclic quadrilateral. I can say that this is true for any quadrilateral. So the quadrilateral formed by angle bisectors of not only cyclic quadrilateral but any quadrilateral is cyclic. Okay, so that the quadrilateral formed by angle bisectors of any quadrilateral is cyclic. Fine. So it is just given that ABCD is a quadrilateral or ABCD is any quadrilateral. Okay, so this is true for any quadrilateral, right? We have never used the fact that ABCD is cyclic. So if you take any quadrilateral, if you draw the angle bisectors, you will get a cyclic quadrilateral PQRS. Fine. Let us move forward. Yeah, prove this question. Pretty straightforward one. If two opposite sides of a cyclic quadrilateral are equal, then prove that other two sides are parallel. So it is given that AB is equals to CD. Okay, opposite sides are equal. We need to prove that other two sides are parallel. That is, AD is parallel to BC. This is what we need to prove. So what I'm doing is I'm joining this AC and BD. Okay. I mean, we also need not join BD. Let us just only join AC. So if you join AC, okay, angle ACB is subtended by chord AB. Okay, angle ACB is subtended by chord AB, and angle CAD is subtended by chord CD. Subtended by chord CD. Now, since these two chords are equal, then I can say that angle subtended by these two chords are also equal, right? Angle ACB is equals to angle CAD. Because yesterday we have studied that equal chords or equal arcs, they subtend equal angles at the center. In fact, that is what is the definition of congruent arcs. The arcs which subtend equal angles at center. And congruent arcs have congruent chords, that is equal chords. So equal chords subtend equal angles at center. So they also subtend equal angles at circumference, because angle at center is nothing but twice the angle of circumference. Okay. So angle ACB is also equal to angle CAD. Now this implies that alternate angles are equal, right? So these are alternate angles. If these two are, two sides and this is a transversal, then these are alternate angles. So this implies that AD is parallel to BC. Fine. So if two opposite sides are equal, then the remaining two sides are parallel. And if two sides of a cyclic quadrilateral are parallel, then remaining two sides are equal and diagonals are also equal. Yeah. Let us prove this one. If two non-parallel sides of a trapezium are equal, then prove that it is cyclic. Okay. So first of all, all of you know what is a trapezium, right? If two opposite sides are parallel, then the quadrilateral is called trapezium. So AB is parallel to CD in a trapezium. So it is given that AB is parallel to CD, and it is given that non-parallel sides of a trapezium are equal. That is, AD is equals to BC. Okay. So we need to prove, it is required to prove that ABCD is cyclic. Okay. So let us do one thing. Let us draw perpendiculars from B and from A onto these sides. Okay. So let us say this point is P and let us say this point is Q. Okay. So draw perpendiculars from A comma B to DC. Okay. Now you can see that AP is equals to BQ, right? Because distance between parallel sides is always same. Distance between parallel sides is always same, right? These two are parallel sides. So these two are nothing but the distances between the parallel sides. So these two are equal. Okay. And also AD is equals to BC because this is given. And angle APD is angle BQC is equals to 90 degrees. So I can say that triangle ADP is congruent to triangle BQC, right? Triangle ADP is congruent to triangle BQC. That is, these two triangles are both congruent. So if these two triangles are congruent, then these two angles must be equal. Okay. So this implies angle D. Okay. Or let me be more specific. Angle ADC is equals to angle BCD. Fine. Also, we know that angle BCD plus angle angle CBA, this is 180 degrees, right? Because these are the co-interior angles. So these angles are co-interior, right? Because these two sides are parallel and this is a transversal. So sum of these two is 180. but this is equal to this. So I can say that sum of these two angles is 180. So this implies angle B plus angle D is 180. Okay. So this means that finally I can say that since this is true, then I can say that this implies ABCD is cyclic. Okay, since there is no space, I'm writing it here. Okay, so because the sum of opposite angles is 180, then we can say that the quadrilateral is a cyclic quadrilateral. Fine. So if in a trapezium, opposite the non-parallel sides are equal, then it is a cyclic trapezium. So in a trapezium in which non-parallel sides are equal, it is called an isosceles trapezium. Fine. So it is equivalent to saying that isosceles trapezium is cyclic. What do you mean by isosceles trapezium? It is a trapezium in which non-parallel sides are equal. Okay. So the isosceles trapezium is always a cyclic one. Okay. So prove that the perpendicular bisectors of a cyclic quadrilateral are concurrent. Prove that the perpendicular bisectors of cyclic quadrilaterals are concurrent. It is also a pretty straightforward one. So let us take a cyclic quadrilateral. So ABCD is cyclic quadrilateral, right? You need to prove that the perpendicular bisectors of these all four sides are concurrent. It means all these four sides, they meet at same point. Okay. So we know that the perpendicular bisector of any chord passes through the center. Okay. So we know that perpendicular bisector of any chord passes through center. So that is all the four perpendicular bisectors passes through center. So all the four perpendicular bisectors pass through center of circle. So this means they are concurrent at center. They are concurrent at center. Fine. So perpendicular bisector of any chord will definitely pass through center of the circle, and so all the four perpendicular bisectors are concurrent at center of the circle. Fine. So these are some of the points which you need to remember about cyclic quadrilateral. So just a quick recap about cyclic quadrilateral. That sum of opposite angles is 180 and exterior angle is opposite interior angle in a cyclic quadrilateral. And the converse is also true, that if in any quadrilateral sum of opposite angles is 180, then it is cyclic. And what's the Ptolemy's theorem? That AB into CD plus AC into plus AD into BC is equals to AC times BD. Sum of product of opposite sides, AB times CD plus AD times BC, is product of diagonals, that is BC times AD. Sorry, AC times BD. So the quadrilateral formed by angle bisectors of cyclic quadrilateral. This is not cyclic quadrilateral, but any quadrilateral. So the quadrilateral formed by angle bisectors of any quadrilateral is cyclic. If two sides of a cyclic quadrilateral are parallel, then remaining two sides are equal and diagonals are also equal. This is what we have proved in the question. So if two sides of a cyclic quadrilateral are parallel, then remaining two sides are equal and diagonals are also equal. If two opposite sides of a cyclic quadrilateral are equal, then other two sides are parallel. This is also we have proved. So a trapezium is a cyclic quadrilateral if and only if it is isosceles. Isosceles means non-parallel sides are equal. Okay. So if in a trapezium non-parallel sides are equal, then this is a cyclic trapezium. And if any trapezium is a cyclic trapezium, then definitely non-parallel sides has to be equal. And a cyclic parallelogram is nothing but a rectangle. So all these things we have proved. So I mean, this fact is very important, the trapezium one. Okay, this fact is very important. Okay, and all these things are very important, the Ptolemy's theorem and the sum of the angles. So I mean, it's better if you remember all these points, but even if you don't remember everything, you should definitely remember this fifth one, this second one, and of course the first one. Okay, so these are some points which you need to remember about cyclic quadrilaterals. Fine, so we'll end this session, and I've already sent you the assignment yesterday itself. So I mean, the assignment is pretty easy. I mean, each question should not take more than 3 minutes. So just try to solve all the questions by today or by tomorrow morning, and you send me the questions which you have not been able to solve, then we'll